Well, hello again. Today we are going to be talking about the chi-square test, and I'm calling it the chi-square test of statistical significance. We could also call it the chi-square test of independence, because we're looking at whether or not two nominal or sometimes ordinal, but we're going to focus on nominal mostly, variables vary in the same way across the different values for that variable. We're just trying to see if there's a level of association, maybe that's another way of saying it, between nominal variables. And so it's kind of an interesting test. We'll also be talking a little bit more about statistical significance and what statistical significance means and how we might walk through that a little more, because I've noticed in class that we have been having some questions about what statistical significance means and how to think about that. So we'll be doing that as well. And if you haven't guessed, my name is Alex Wiseman, and actually I'm very interested in this topic, so I'm looking forward to going through it with you. It's really a pretty common thing to do a cross-tabulation. In other words, you have two variables. In this case, we have age and we have student status. Right? Those are our two variables. And we've simply made a table for age categories and then student status categories. And we've tabulated the percentage of people in our data set, our imaginary data set at this point, that fall within each of these categories or cells where a value of age and a value of student status overlap. So 88% of 15 and under students are full-time. Right? 95% of 16 to 18-year-olds are full-time. None of the 16 to 18-year-olds are part-time, and 5% of the 16 to 18-year-olds are not a student. And then we can total up the numbers under each of these, or for each of these categories. We could also do it down here if we wanted to, but we haven't. Anyway, it's one way for us to think about, well, who is a student based on their age? And you can see that when people are young, and they've been highlighted in red to make this pretty obvious, that they're more likely to be a full-time student. And when people are older, they are less likely to be a student or more likely to not be a student. And so we see that there's some association between age and student. And we're looking at age categories here, and we're looking at student categories. Right? Well, a cross-tabulation can roughly determine if there's a relationship between two variables, but we want to use tests of statistical significance, particularly with some nominal variables, to see if there is a relationship in the larger population from which our sample was selected. In other words, could we say that based on our sample, if we have a representative sample for our population, that if there's an association between two variables in our sample, it's likely that there's an association between those two variables in the larger population. In other words, how much can we extrapolate or infer about the larger population from our sample data? And as we've talked before, there are a couple of ways we talk about this level of statistical significance. We simply say that significance level is the probability that a relationship found in sample data occurs by chance, even if there is really no relationship in the population sampled. Right? So how likely is it that we're going to find a relationship or find a difference in our sample if there's no relationship in the population that's sampled? And our significance level can vary anywhere between 0 to 1. It's usually a proportion, and we call it a probability or a p-value, right? And as we've talked in class before, there's a 5 in 100 chance, which we usually use as our threshold, and that's represented as p. Usually we say p is less than 0.05. And we're always looking for a probability or a significance level of less than 0.05. That'd be a 5% chance that we're finding something in the sample that doesn't exist in the population. In other words, we're incorrectly saying that there's something going on. And you can see that the p equals 0.01 is 1 out of 100, or 1% chance. P equals 0.001 is 1 out of 1,000, etc. And the normal curve, which we've talked about on many occasions, provides us with a basis for understanding the probability associated with any possible outcome. And the study of probability is the basis for determining our degree of confidence that we have in stating that a particular finding or outcome is true, or at least is supported by the data. I'm a little wary of using the word true. And we're usually trying to say that it falls on these extreme tails of our distribution, right? If we can limit it to the 2.5% chance that it's on either end, which would add up to be 5% total, right? Then we feel pretty confident. So for example, if we were playing a game of rock, paper, scissors between two players, we could actually calculate the probability that player A would beat player B by using something like this. If we just know what the combinations are for player A and player B for rock, paper, and scissors, then we can start to envision and estimate which player is going to be more likely to win the game. So tests of statistical significance report on the probability that we would find a relationship as strong as the one in our sample data if there is no prior relationship in the population from which the sample was drawn. In other words, is there something really going on? Now, hypothesis testing is a way that we can state our assumptions about a population parameter. Remember that there are parameters for populations and statistics for samples from those populations. So hypothesis testing involves making an assumption about a population parameter and then determining whether or not a sample mean differs enough from the assumed value of the population parameter to allow us to reject the null hypothesis. And a null hypothesis is simply stated like this: the population parameter is the same as what we're finding in our sample. That's the equal sign, the same as. The alternative hypothesis is simply that they are not equal. It is that straightforward, and some of you have already been using this. So let's quiz ourselves a little bit. What is a null hypothesis? Is it a statement of inequality between two variables, a statement of correlation between two variables, a statement of equality between two variables, or a statement summarizing an experiment? What do you think the answer is? Feel free to pause if you want to try to figure it out before we get the answer. Okay, the answer is it's a statement of equality between two variables. Right? The null hypothesis is a statement of equality between two variables. Remember, sorry, I did that wrong. Population parameter equals the sample. Okay, how about this one? A statement reflecting that two or more things are equal to or unrelated to each other is called a research hypothesis, a research speculative postulation, a null hypothesis, or an alternative hypothesis. So what is a statement reflecting that two or more things are equal to or unrelated to each other? You ready? Well, it's the null hypothesis again, right? Because there's no difference. Next, the null hypothesis acts as both a what and a what against which the actual outcomes of the study can be measured. Is the null hypothesis both a question and a postulation? Is it both a question and an answer? Is it both an outcome measure and a research question? Or is it both a starting point and a benchmark against which the actual outcomes of the study can be measured? The answer is it's a starting point and a benchmark. So the null hypothesis acts as both a starting point and a benchmark against which the actual outcomes of the study can be measured. That means that we start by saying, you know what? We're just going to play it safe. And we're going to assume that nothing is happening here. There's no relationship, that everything's equal, right? Nothing unique. And then we use it later as we collect the data and we analyze the data as a benchmark. If we start with our benchmark that nothing is happening, then anything that deviates from nothing is happening becomes an alternative hypothesis, becomes our alternative finding. So we can use this null hypothesis to start and then to benchmark. So which of the following is an example of a null hypothesis? Would it be that high SAT scores are strongly correlated with high GPA scores? Would it be that the weight gain of rats on a low-fat diet is not different from that of rats on a high-fat diet? Or would it be that phonetics tutoring improves reading ability? Or that driving under the influence of alcohol causes accidents? Well, let's just think through this a little bit. If a null hypothesis means that there is nothing going on, or that two things are the same or equal, all right, strongly correlated, something's going on. Improves reading ability, something's going on. Causes accidents, something's going on. But in this one, is not different from. Do you see the equal sign in there? Right? Lo and behold, that is the null hypothesis. So how would we write the following statement as a null hypothesis equation? By the way, I'll never ask you to do this in class, but I do want you to be familiar with some of the notation that's used. And it's a good way to think about what we might be doing. If we said that there was no difference between IQ scores of students at TU, which can be any university you want that begins with a T, and Harvard students, we would write it that the population mean of TU students and the population mean of Harvard students equal each other. This leads us to think about our type 1 and type 2 errors. And you've heard me say on more than one occasion that our p-value is estimating our probability of committing a type 1 error. That means that the null hypothesis is true, but we are rejecting it by saying that something is going on when it really isn't, because the null hypothesis is true. This is our false claim error. A type 2 error is when the null hypothesis is false, meaning that something really is going on, but we don't reject it. That's sometimes called the failure of detection. And it's important, in addition to the p-value, we also sometimes look at alpha levels, and that's the Greek symbol for alpha. So this is an alpha error, making a false claim, or a type 1 error. So now you know where that terminology comes from. Okay, so what is the risk set by the researcher for rejecting a null hypothesis when it is true? Is it called experimental error, error significance, significance level, or error level? Well, we usually call it the significance level, right? That's where we started with our slides so far today. If we reject a null hypothesis when in reality there is no difference between two groups, have we made a type 1 error, a type 2 error, a type 3 error, or no error at all? Well, we've made a type 1 error, right? The false claim. We have rejected the null hypothesis and said that something is happening when in reality the null hypothesis is correct, or at least there's no evidence to say that it isn't. By the way, type 3 error, made it up. If you accept the null hypothesis when in reality there is a difference between two groups, then you have made a type 2 error. This is failure to detect, or failure of detection. So you've said, yep, the null hypothesis seems to be what's happening, when in reality there really is a difference, or there's an association. Right? Then you've made a type 2 error. But we are almost always interested in the type 1 error. If you accept the null hypothesis when in reality there is no difference between two groups, then you have done the right thing. You haven't made any error. The null hypothesis seems to be supported by the evidence, and you have said that there is, or you have found that there's no difference between our groups, or no association between our variables. You've done the right thing and not made any error. If you reject the null hypothesis when in reality there is a difference between two groups, then what? Type 1, type 2, type 3, or no error? Hey, guess what? You, again, have not made an error, because you have rejected the null hypothesis when indeed there is a reason to reject it, because there is a difference between two groups, or two variables, or an association there. The statement, the probability of observing an outcome different from the one here is less than 5%, can also be written that p is less than 0.05. And then finally, if a researcher sets the decision rule p-value at 0.01, what is the probability of making a type 1 error? Well, it's 1%, because it's 1 out of 100. We will come back and continue with significance testing in just a minute.